Dear students, I am Dr. Sunita Meena, scientist in Animal Biochemistry Division of National Dairy Research Institute located at Karnal in Haryana. Today, I am going to teach you about the introductory part of spectrofluorimetry under paper Biochemical Techniques. Radiation of a particular wavelength excites an electron and energy transition may occur in different vibrational levels of a particular excited state because the energy of the vibrational level of excited state matches with the energy of vibrational level of ground state. Therefore, in such energy transitions, some energy is lost as heat, also known as non-radiative transition, until it reaches the lowest vibrational level of the excited state. After losing some energy as non-radiative transition and reaching the lowest vibrational level of the excited state, the electrons follow radiative transition. Radiative transition occurs when electrons falls back from higher energy excited state to lower energy ground state within the molecule. Then energy emitted is measured as light or fluorescence. In this presentation, my main focus will be on the principle of fluorescence spectroscopy. With this presentation, I would like to highlight the basis of fluorescence, the electronic transition which leads to fluorescence by the fluors, differences between the intrinsic and extrinsic fluors and their quantum efficiency will be discussed. I will cover the types of illumination setups in the instrumentation part. Their advantages and disadvantages will also be discussed. Finally, I will be covering the application part of the fluorescence spectroscopy. Fluorescence spectroscopy is also known as fluorimetry or spectrofluorimetry. It is a technique to detect and analyze the fluorescence in the sample. Fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation. This substance which is emitting the fluorescence is known as fluor or fluorophore. In this emission phenomena, a beam of light excites the electron in a molecule which moves from ground state to higher energy excited state. When the electron falls back to the ground state, it emits the wavelength in the visible region, also described as fluorescence. Fluorescence spectroscopy is mainly concerned with the electronic state and vibrational states. Therefore, in most cases, the emitted light has a longer wavelength having lower energy than the absorbed radiation having higher energy. A fascinating example of fluorescence is when the absorbed radiation of electromagnetic spectrum is in the ultraviolet region, which is invisible to the human eye, and the emitted light is in the visible region. It is a form of luminescence when the emitted light is in the visible range. During radiative transition, the electrons may descend into any of the several vibrational levels in the ground state. As a result, the emitted photons will have different energies and thus different frequencies. Stokes shift is named after Irish physicist George G. It is the difference between the wavelength of absorption maxima and emission maxima. Wavelength of absorbed radiation having lower wavelength units and higher energy is denoted by A. Wavelength of emitted radiation or fluorescence having higher wavelength unit values and lower energy is denoted by B. Therefore, Stokes shift is equal to B minus A. Good results are achieved with the compounds have the greater Stokes shift. Greater the Stokes shift, lesser will be the interference as the excitation and the emission spectra do not overlap. Chromophores which exhibits the phenomenon of fluorescence are called fluors or fluorophores. Fluorophores are organic molecules of 20 to 100 Daltons. As already discussed, some fluorescent molecules absorbs the electromagnetic radiation in visible region and emits the radiation at a higher wavelength in the visible region. But most commonly, fluorescent molecule absorbs the electromagnetic radiation in the UV range and emits in the visible range. Intrinsic fluors are the native compounds exhibiting the property due to the presence of aromatic groups in amino acid side chains in the case of proteins, for example, tyrosine, tryptophan and phenylalanine. Cofactors such as FMN, FAD and NAD also exhibits fluorescence. Extrinsic fluors are non-fluorescent compounds which can be detected by coupling a fluorescent probe. Examples are 1-anilino, 8-naphthalene sulfonate and fluorescein for proteins, ethidium bromide and acridin orange for DNA. Fluors have characteristic emission spectrum called fluorescence as well as characteristic absorbance spectrum which depends upon its structure and chemical environment. Most electrons will occupy the ground state and lowest vibrational level denoted by S0 and V0 at room temperature. Electrons are elevated to the high energy excitation states S1, S2, etc. by the absorption of photons provided by the electromagnetic radiation. The excitation occurs in less than 10 to the raised power minus 15 seconds. The lifetime of excited state is very short, ranging from 0.5 to 8 nanoseconds. Non-radiative transition moves the electrons to the lowest vibrational energy in the lowest excited state S1 V0. Electrons after reaching the lowest vibrational level of the excited state returns to the ground state in less than 10 to the raised power minus 8 seconds and the emitted energy is stated as fluorescence. Quantum efficiency denoted by capital Q is the ratio of quanta fluoresced and quanta absorbed or ratio of number of photons emitted and number of photons absorbed. It is independent of the excitation wavelength. Spectrofluorimetry exhibits accuracy with fluorescent samples present at low concentration. At low concentrations, the intensity of fluorescence IF is related to the intensity of incident radiation I0 by IF is equal to 2.3 into I0 into epsilon lambda into C into L into Q. In this relation, fluorescence intensity is directly proportional to the concentration where C is concentration of fluorescing solution, L is light path of fluorescing solution, epsilon lambda is molar extinction coefficient for the absorbing material at wavelength lambda. Fluorescence is susceptible to pH, temperature and solvent polarity. Whether a particular compound will fluoresce or not is the main problem being encountered. Fluorescence quenching occurs when emitted fluorescence is lost to other molecules by collision interaction. Quenching is more in concentrated samples and therefore it decreases the sensitivity. To increase the sensitivity and accuracy of spectrofluorimeter, very low concentrated samples should be used which decrease the collisions and hence the quenching. Many interfering materials such as detergents, filter paper and some tissue materials may affect the fluorescence. Coming to the instrumentation part of spectrofluorimeter, light source can be mercury lamp emits light near peak wavelengths. Xenon arc exhibits continuous emission spectrum with constant intensity at 300 to 800 nanometer range, but can also used for just above 200 nanometer. Most common types of monochromators utilizes a diffraction grating. Two monochromators are used. One monochromator for excitation and second monochromator for emission. This figure shows the 90-degree illumination setup. One monochromator, which is also known as excitation monochromator, is used for the selection of excitation wavelength from incident beam. Fluorescent sample will emit the fluorescence in all the directions. In this setup, angle of 90 degree is chosen for emitted fluorescence. Second monochromator, which is the emission monochromator, is used for the determination of fluorescence spectrum. The excitation wavelengths which are frequently being selected are in the ultraviolet region and the emission wavelength is in the visible region. Pre-filter effects arises due to the absorption of radiation before reaching to the fluorescent molecule, and post-filter effects arises due to the decrease in fluorescence emitted by the fluorescent molecule before escaping the cuvette. These effects increases with the increase in sample concentration. The use of microcuvettes alleviates these effects to some extent. Front phase illumination setup removes pre and post filter effects. In front phase illumination, cuvette with one optical phase is used and the excitation and the emission occurs at the same phase. This setup is less sensitive than 90-degree illumination setup. Up till now, we have discussed the principle of spectrofluorimeter. Good results are achieved with fluors having greater Stokes shift as there is less interference between excitation and emission spectra. The efficiency or intensity of fluorescence is directly proportional to the concentration, light path, molar extinction coefficient of fluorescing solution. We have also discussed the instrumentation part where mercury lamp or xenon arc are used as light source. Two monochromators are used and these are called excitation monochromator for selection of excitation wavelength and emission monochromator for determination of fluorescence. There are two types of illumination setup, 90-degree illumination and front face illumination. Fluorescent probes are useful in both qualitative and quantitative detection. It helps in the detection of biological compound which is present in very low concentration in a mixture. They are applied to characterize folding intermediates and surface hydrophobicity. The intrinsic fluors such as tryptophan, tyrosine and phenylalanine present in the protein are responsible for the fluorescence exhibited by the proteins. Proteins are generally excited at 280 nanometer and fluorescence is measured at 295 nanometer. The fluorescence of folded protein is contributed by all individual aromatic amino acids present in it. Among these, tryptophan exhibits strong fluorescence whereas tyrosine and phenylalanine exhibits less fluorescence. The emission fluorescence of tryptophan is solvent dependent. As the polarity of the solvent surrounding the tryptophan decreases, the fluorescence intensity of the tryptophan increases. Tyrosine emits fluorescence less than the tryptophan and its fluorescence is quenched by the tryptophan present in its vicinity. Phenylalanine gives weak fluorescence and its fluorescence is only observed when both tyrosine and tryptophan are absent. Cofactors such as FMN, FAD, NAD exhibits the fluorescence and are also applied in the protein structural studies. The binding and release of inhibitors, substrates at sites close to the fluor cause changes in the conformation and thus changes the fluorescence spectra. Any conformational change in the protein therefore changes the absorbance. It can also be used to study the denaturation and aggregation of proteins and peptides. The fluorescence intensity of a fluorescently labeled molecule is dependent upon the solvent or environment in which it is present. Changes in the pH or solvent polarity affects the conformation, and therefore structural changes can be monitored by the changes in the fluorescence. Extrinsic fluor ANS 1-anilino 8-naphthalene sulfonate probe can be used to monitor the changes in the mitochondrial membranes during energy transduction. Hydrophilic and hydrophobic probes can be used for the membrane structure studies, as they can orient themselves in the hydrophilic and hydrophobic regions of the membrane and gives the information regarding the properties of the membrane and its surface. Phospholipids containing 12,9-anthroanoyl stearic acid and 2,9-anthroanoyl palmitic acid into membranes yield the information about the thickness of the membrane. 12,9-anthroanoyl stearic acid and 2,9-anthroanoyl palmitic acid, when present in the membranes, indicates the regions 0.5 nanometer and 1.5 nanometer respectively from the phosphate head groups of the lipid bilayer. FRAP, that is fluorescence recovery after photobleaching technique, is used for measuring the lateral diffusion in layers or thin membranes by fluorescent probes. The sample under study is fluorescently labeled. Fluorescence is measured in sample and the image is observed and captured with the help of optical microscope equipped with timeline camera. Light source is focused on small patch of the sample and exposed to high intensity illumination, which causes photobleaching of fluorescent probes. Photobleaching permanently loses the ability of fluor to fluoresce. This turns the patch into dark color. Fluorescence intensity in this area decreases and the image of the sample is continuously observed in the microscope. With time, the adjacent and nearby fluorescing probes will slowly diffuse into the dark patch as Brownian motion proceeds. The motion of these phospholipids or proteins in the membrane can be studied by monitoring with low intensity radiation. Depending upon the speed of diffusion and time, the dark patch will fluoresce again as the fluorescent probes moved into the bleached area of non-fluorescent probes or bleached probes. FRAP technique is very useful for studying the diffusion. Fluorescently labeled phospholipids or proteins may be incorporated into biological membrane and subjected to the similar treatment. It is used to study the protein binding in cell membrane, cell surface characterization, and free energy in phospholipid layer can also be studied. Energy may be transferred from donor to acceptor fluor through fluorescence resonance energy transfer called FRET, or electronic energy transfer, or dipole-dipole coupling. For this to happen, the distance between the donor and acceptor is critical and both the fluors must be situated closely. There must be overlap between the donor fluorescence spectrum and acceptor fluorescence spectrum. When the donor fluor is present alone, it will fluoresce. Placing the acceptor fluor in the vicinity of donor fluor, acceptor fluor quenches the fluorescence emitted by the donor fluor. This emitted radiation by donor fluor is sufficient for the electronic transitions in the acceptor fluor and thus emits the fluorescence of different intensity. This technique detects very small changes in distance, detects molecular interactions in different systems, localization of metals in metalloproteins, detects the interaction between the proteins, measurement of conformational changes during binding of enzymes with substrate and receptors with ligand. It is used to measure the distance between the two domains in the same protein and also gives information about lipid rafts in the cell membranes. Fluorescence immunoassay is a sophisticated technique and is used to detect the antigen and antibody interactions by using the fluorescent probes to label either antigen or antibody. Antigen is detected by the binding of primary antibody. Excess of the primary antibody can be removed by washing. The antigen-antibody complex is then detected by the secondary antibody labeled with the fluor. Excess of the labeled secondary antibody can be removed by washing. The fluor is excited at a particular wavelength and the fluorescence is detected by the spectrofluorimetry. High background fluorescence is the major disadvantage of this technique. Two approaches are followed to reduce the background fluorescence and increases the sensitivity. First, fluors having large Stokes shift should be preferred. Example, europium chelates. And secondly, well-designed fluorimeters should be used, which delays the detection of emitted light, and meanwhile the background fluorescence will decline. Fluorescence activated cell sorter is a type of flow cytometry. It is the method of physical separation or sorting of cells from a mixture of cells or cell suspension into different compartments, which is based on the fluorescence and light scattering emitted by the cells tagged with different fluors. A cell suspension is allowed to pass through a narrow nozzle in a stream of liquid. This fast flowing stream of liquid is broken into droplets and each droplet contains a single cell which is achieved by vibration. One cell in one droplet then passes through the fluorescence detection apparatus which senses the fluorescence characteristic of a particular cell. Additionally, each droplet also passes through an electric charging ring which give the charges to the droplet. The charges depends upon the fluorescence emitted by the cell. These charged droplets then passes through an electrostatic deflection system which senses the charges on the droplet and physically separate or deflects the droplets into sequentially arranged containers. This technique is used for counting the cells, separation of cells and purification of cells from a mixture. A spectrofluorimeter, which is equipped with microscope, enables to observe the binding of antibody to a single bacterial cell or subcellular organelle and also helps in the identification of cancerous cells from normal cells, as they express different set of proteins for which fluorescent labeled specific antibody can be applied. Since some malignant cells have more nucleic acid content than do normal cells have, therefore, these malignant cells take up more acridine orange dye which binds to the DNA and can be differentiated from the normal cells. Dear students, spectrofluorimetry is a technique for measuring fluorescence. This is one of the very sensitive method for assaying analytes. As I have explained, this technique is very useful for studying peptides, proteins, membrane structures, protein-protein interactions, conformational changes, protein binding in cell membrane and metal localization in metalloproteins. It is also useful in studies which includes molecular interactions, diffusion of phospholipids and proteins, detects small changes in distance and also used for counting, separation and purification of cells. Dear students, I hope this presentation helped you to understand the basic concepts of fluorescence spectroscopy. Thank you students for watching this video on EPG Pathshala.